Okay, so today what we're going to do is we're going to spend probably 30 minutes going over some key points of Chapter 20, and then we'll spend about 30 minutes going over the review for the final exam. So we won't be here till 1:20. If it's 1 o'clock, somebody start pointing at the watch. Okay, so give me a hint that we can make this go quicker. So the last thing we talked about was the radioactive rays and their ability to penetrate. One of the things that you need to know is that alpha particles go the least penetrating, but they cause the most damage. Beta particles penetrate a little deeper, they cause less damage, and the gamma particles penetrate, go right through you. Most of them do, but they do very little damage. Okay, so that's kind of the synopsis of the radioactive particles. So of the what we think are non-traditional particles, we look at things like a positron. So we talked about the elementary particles of an atom, an electron, a proton, and a neutron. We never mentioned positrons. So positrons are the result of a nuclear event. And again, a positron is something that's a charge of a +1, but it has the characteristics of an electron in that it acts like a wave, all right, but well as having mass. And the way we describe it is it's an antiparticle of an electron. It's the opposite of what an electron would be in terms of charge, similar mass. They're similar to beta particles in their ability to penetrate and to be ionizing radiation, meaning they can kick electrons off. And positrons result from the loss in a nucleus. So when a positron is lost out, that means the mass number remains the same, but the atomic number decreases to 1. So this is when a positron is going to emission is going to be when a neutron decays to form this positron plus an electron, and the electron is given off in an ionization event. But because there's now the same number of protons plus neutrons, in this example, phosphorus 30 does a positron emission, and it converts to silicon 30. The total of protons and neutrons is still the same. What varied now is because we lost a proton. We varied the number of protons. I said that. Get that wrong. It's we're changing the number of protons. We've changed the atomic number of the matter. So no longer is it phosphorus anymore. We changed the proton into a neutron. So this is get that backwards. We change a proton into a neutron and lose the charge out of it. Okay, so another example of a nuclear event that's not a traditional type of event that can occur, and this one's pretty rare. This is called electron capture. And what happens with electron capture is when an inner orbital of an electron is pulled into the nucleus. And you have to go back and think about what we started talking about at the end of Gen Chem 1. And we talked about where the electrons lie with the probabilities that we had. And we talked about these inner electrons. So this was distance from the nucleus, and this was the probability. These inner electrons, some of them are very close to the nucleus. All right, so what happens with these 1s electrons? They get so close to the nucleus, at some point, some of them are attracted to the positively charged in the nucleus enough that they collapse into the nucleus. As soon as it crosses that threshold, there's a condensation and the electron collapses down. What it results in is an emission that's similar to a positron emission, and that it gives off some energy, but there's not a particle associated with it. What's happening now is a proton combines with the electron, and it makes a neutron in it. So now we've got an extra neutron. The number of protons goes down by 1. In the example of ruthenium-92, it has 44 protons initially, but one of the protons gets converted into a neutron, so it converts to technetium-43, but there's still a mass number of 92. The number of protons plus neutrons stays the same. And that, as we talked about, that conservation of mass, in all of these cases, all of these things have to add up. We've got to get all the things adding up. And in some cases, like this one, it's a minus where it's going down to the other side. If you're going to spend any time memorizing anything in this chapter, here's what I'd tell you to spend 5 minutes to work on this. It's the modes of decay, and it summarizes the different types of decay and what happens with the charge associated with it. And we've talked about every one of these just on one slide: an alpha decay, a beta decay, a gamma decay. The positron and electron capture emissions are ones that we introduced today. But the key thing is to understand what's happening to the A and the Z. Are they going up or down? And what happens to the N over Z ratio? We're going to talk about its importance in just a moment in a few slides. All right, so why does this occur? Why are some atoms, combinations of protons and neutrons, more stable than others? And that goes back to the nuclear force, the attractive force of the nucleus, that's called the strong force. And this force is only found inside of a nucleus. Now, we talk about electrostatic forces, and we talk about mechanical forces where you're physically pushing something. And we've talked about chemical energy and all these different types of energy. Electromagnetic radiation is a form of energy. This nuclear force is different, the strong force. And it's something that really we struggled to understand in early chemistry. Why, once Rutherford realized that there's this tiny nucleus, we didn't have a good explanation for a long time of why that nucleus stayed together and why it doesn't fly apart into pieces. Okay, so the describing factor in this that came from quantum mechanics, and Einstein played a role in that description, was what's called the strong force. And this is a force that acts over very, very, very short distances. So when I'm talking about that, it's a fraction of a neutron, a fraction of an angstrom. So we talk about a typical bond length as an angstrom, 10 to the minus 10th. This is a force that acts in the neighborhood of 10 to the minus 11th to 10 to the minus 13th meters. Things really have to be close together, or this force dissipates where it's so much it doesn't even matter. And remember, we called the things inside of the nucleus nucleons, the protons and neutrons. And what happens is the neutrons play a critical role in the stabilizing of the nucleus. What they do is they add to the strong force. Yet, unlike protons, they don't repel each other. You put more protons in there, the protons don't want to be close to one another. You add these neutral particles in there, they're the glue that holds the nucleus together. That's the role of a neutron. So, in this mysterious thing of an atom, it has a critical role. Now, there's something called the N over Z ratio. And the N over Z ratio is simply the ratio of the number of neutrons to the number of protons for the various isotopes. And it's an important measure of the stability of a nucleus. Is this a combination that's going to stay together, or is it not? What happens if the N over Z ratio is too high? The neutrons are converted into protons via beta decay. So that element's radioactive if it's too high. If the N over Z ratio is too low, the protons get converted into neutrons by positron emission or electron capture, and then you have something that is also radioactive. So what it means is that there is a perfect amount of protons or neutrons that you want to have. And this has got a unique name. It's called the Valley of Stability. So the green dots that are in this represent the stable isotopes, or the combinations that we find that are stable and non-radioactive. The ones that are the yellow dots represent that all the isotopes that exist for a given element. Right? Now, some of them are not very abundant at all. Okay, they're very, very low abundance, but they can be created or they have been created on the surface of the Earth. Now, if you look at the line, the deviation is that ratio doesn't just want to be 1. All right? It starts off in the small elements and it tracks along with 1 very well, and then it makes a bow upwards, that bend upwards. And it tends to be a little bit beyond 1. So we go to our heaviest elements, things like the mercury atom. The most stable isotope, the N/Z ratio is 1.5. So that means there's 50% neutrons, more neutrons than there are protons in the nucleus. That's because an atom that big requires that much. You want to think of it as the glue, keep it sticking together. Otherwise, all those positive charges want to repulse away from each other. It causes the stability of the nucleus. And as you go to smaller and smaller atoms, you'll see that ratio gets smaller and smaller. And by the time we get to something like carbon-12, it's a ratio, N/Z ratio of 1. Right? So carbon-12, 6 protons, 6 neutrons. I mean, so it's something that varies throughout the mass of the element. So we can't say there's a perfect number. There are some odd occurrences that occur with it. So if we look at things that have Z above 83, so we go to atomic number 83, everything above 83, this is kind of the limit. There's nothing that's a stable isotope above 83. If you look at everything above 83, and all the ones at the top above 83, they're all in parentheses. That means those are all radioactive elements. So kind of 83 is the biggest element that we can have and still be stable or non-radioactive. Everything else is radioactive above that point. So there's a lot of elements that are available. So this periodic table shows up to element 118. This is our newer periodic table. But everything above 83, the last 30 or so, 35, are all radioactive elements. So we don't necessarily want to be around those. All right, there are some oddities, and the term that the book uses is magic numbers. Besides the N/Z ratio, there seem to be some trends associated with the actual numbers of protons and neutrons that have an influence on stability. And there's a lot of theories on what this is. What happens if we have a stable nuclei commonly? If we have an even number of protons and neutrons, they're stable. So this is a table that's out of the book. If we look at the number of isotopes that are stable, 157 of them have a combination that's an even number. Now, we don't have a good explanation of why that is. It's one of those things we're going to learn later. We just don't understand that. Only 5 have stable combinations that are odd. And if you look at probability statistics, you got positive charged particles and neutral particles. It should be 50-50. I mean, it should be an even number. If this is 157, this should be 157 if it's just random statistics. So something's guiding the nucleus towards stability with that, and we don't understand a total picture of everything that's going on there. One of y'all are going to discover that. This is one of the reasons that we're actually trying to look at things like what is the glue that holds the nucleus together in more detail. So one of the big studies that's been going on in the last 20 years is a project with CERN in Europe. And they've been looking at, they built a device which is the largest machine in the world called the Large Hadron Collider. All right, so the LCH was devised to try to apply enough energy into atom to break it into the particles that make up. Now you're actually looking at the particles that make up these positrons and the other subatomic particles, and they're looking at something called quarks. And they're looking for something called the dark quark. They're looking at dark matter. And the reason that's of great concern to us, because not only can it help us maybe solve this mystery of what's holding things together, but if we look at the energy or the matter in the universe, what we've become aware of in the last 10 years is that we can only see about 20% of the matter in the universe. The other 80%, 70 to 80%, is in a form we can't visualize. And we don't really know what that form is. We don't understand it well. And one of the big questions we have is how much matter is in the universe, Not that it matters in our lifetime, but in eons to come, if there's enough mass in the universe is going to stop expanding and it's going to crush back down if there's enough gravity to pull it back together. If there's not enough matter, it's going to continue expanding indefinitely or forever. Okay, so that's one of the things in physics we're trying to answer. So who significantly died? What significant person died in physics in the last month? Okay, so Hawkins, it came out yesterday, his last paper was rushed through publication that he was working on. So his concept, this paper was talking about what are the possibilities of multiverses. So he was suggesting that in Hawkins is that the universe that we live in, there is an infinite number of parallel universes that coexist. All right, and that's pretty complex. I use the term cosmology, but to think that in another dimension in the same space we are, there's another class of students doing the same thing. I hope they enjoy their last day of class. So I don't know, but there's an infinite number of possibilities. If you read sci-fi, you can find dozens of authors that have taken on that concept of multiple dimensions and how possibly we could go back and forth in between those. One of the theories is that black holes that all this matter runs into is that the matter that runs in a black hole falls out into another dimension. It's one of the things we don't understand. At the center of the Milky Way, there is a massive black hole that is swallowing trillions of tons of matter every second. And it just seems to disappear. It concentrates to a single point called singularity, and then we think it goes through a wormhole. And the theory is, and again, it's complete theory because nobody's been through one of these things. We don't have any evidence of what's happening on the other side, but it comes out in another dimension. Okay, it's theory, and that's you can read Hawking's work, and you can get there's a number of people. He wasn't alone in proposing this, but it gets we get it pretty insignificant pretty quick when you start thinking about an infinite number of universes that could be coexisting. All right, so oddities. There are certainly oddities associated with the stability of isotopes. If we look at the idea of the stability, if there are things that have an N over Z of 2, 8, 28, 50 and 82, or 126, that's when we have the most stability. And things like the octet rule seem to follow in the same principle. And we don't have a solid foundation of why. All right, we're going to spend a little bit of talking about the things that do decay. So we said everything with an atomic number greater than 83 is a radioactive element. And that may be a final exam question. Which one of the following elements is radioactive? 83 is your magic number. Okay, now there are a couple of things that are below 83 that are radioactive, but everything that above 83 is radioactive. So what happens when something's radioactive? It means that one of the nuclides, one of the isotopes, is changing into another isotope during this decay process. And what happens is that isotopes will continue to decay until finally you reach something that's stable. And this is called the decay series. And we'll look at one example here. This is the example of the decay of uranium-238. So 238 is the common form of uranium, and it's fairly stable. And I say fairly stable, it has a long half-life. Okay? It's not so radioactive. You can pick up 238 and you can hold it in your hands and you're not going to die of radiation poisoning. But it gives off some energy that you can detect. You put it on a piece of X-ray film, the energy from that will cause a signal on the film. But just to give you an idea of the number of transitions that occur, this table represents an alpha decay if the line goes to the left, and a beta decay if the line goes to the right. It'd be your left and your right. So it goes from 238 to thorium-234, to francium-234, to uranium-234, to
to thorium-230, and it continues all these different combinations and alpha and beta decays until it gets something stable, and that stable thing's lead-206. But I mean, there's a dozen intermediates in here that are involved in the radioactive decay. So that's one of the things that they can look at in terms of nuclear materials. They don't just look at the presence of what is the radioactive isotope. They look at all these other isotopes. The name for these, it's on the next page. They're called daughters. All of these daughter isotopes are present, and what are their abundance tells us something about the state of that decay and how long has it been since that element has been created. The wrong way. All right, so when we look at the decay process, the rate of the decay is how fast the isotope is changing, and it's changing at a constant rate, but it varies for each one of the isotopes. So the same way that we talked about kinetics with chemical reactions, we can talk about the kinetics associated with these nuclear events, the length of time that it takes an element to lose half of its radioactivity. That's defined as a half-life, and it's a constant value. And the radioactivity process follows what we call first-order kinetics with chemistry. All right, so with first-order kinetics, as with all kinetics, the things that makes radioactivity different, kinetics is function of temperature, and we used changes in temperature to measure the activation energy. Radioactivity is completely independent of temperature. And I'll say that it changes when temperatures exceed 10,000 degrees Celsius. So until then, it doesn't matter. All right, so 10,000 degrees Celsius is approaching the energy or the temperature inside the core of the sun. But at the temperatures that we're talking about, that we live in and can develop in chemical systems, it's a non-factor whatsoever. All right, so rate is equal to the rate constant times the number of nuclei that you have. The half-life, if you remember from first-order kinetics, was this constant, 0.693 divided by the rate constant K. So what it means is that for something that has a shorter half-life, that means more of those nuclei are decomposing every second, and the word that we use to describe it is hotter. And we want to stay away from hot radioactive species. That means they have a strong or highly energetic radioactive emission. There's a lot of energetic events per second occurring. Now, saying something's radioactive can mean a lot of different things. And this is an example of some different nuclides and how radioactive they are and how quick the emissions they are. So if we look at thorium-232, it has a half-life, an alpha emission, of 10 to the 10th years. So in our lifetime, let's say you live to be a ripe age of 100, there's almost no change. If you have a gram of it in your lifetime, there's still a gram of it left. All right? If you look at uranium-238, the most stable form of uranium, it's very similar. It's a billion years, 10 to the 9. Not very radioactive. If we look at C14, the thing that we use for radiocarbon dating, though, much quicker process. This is a beta emission. It's 5,700 years. But then you look at things that now are highly radioactive. So radon-220, its half-life is less than a minute. I start off with a gram of it. In a minute, I got half a gram. All right, it's going to continue to decay. So if you did that in a matter of, look at a period of a day, it's all practically gone. And then you have some of those intermediates in that chart that are only exist for the blink of an eye. So thorium-129, it has a half-life of a microsecond. Maybe it's gone. Right? And a lot of the elements that are man-made, so as soon as you start going beyond element 93, almost all of those elements are completely man-made. They don't exist in any abundance on the surface of the Earth. All the plutonium, element 94, everything above 94, we've made it in a lab. And some of these things, it took us so long to name some of these things. So if we look at these two different periodic tables, which were printed 5 years apart, right, we knew about these elements since the 1960s. Some of them were only made, some of these very latest ones were only made in the last few years, the last 10 years to 20 years, but we couldn't come up with a common name because there was an argument on, is that really the element? Okay, if it's not stable on its own for more than a microsecond, do we even call that something that's stable matter? And the final decision was yes. If we know that there was that combination remade of protons and neutrons, and we had something for some point in time that had this many number of protons in it, we say that element could exist at that period of time. Now, will there be another period added to the bottom? I don't know. It depends if we come up with more energetic reactions, and it could be a remote possibility that we haven't discovered something yet. So looking at the radioactive decay of radon, the one I mentioned, its half-life is 55 seconds. So if you started with 1 million of it, you're down to, in 1 minute, less than 1 million of them. But if you go to 10 minutes, you're down to just a couple of them. All right, that's the radioactive decay. So if we're dealing with radiation, something like a nuclear event, in terms of an atomic weapon, we don't want to use atomic weapons. That's our goal not to, if we're sane. But a bomb like the radioactive bomb of uranium that was dropped on Hiroshima or Nagasaki, either one of them, it left radioactive plutonium or radioactive uranium or those daughters from that, and those are still detectable today, the background radiation. I mean, those things are still there in high levels. And if you look at one of the, probably the biggest eco-disasters that we're dealing with in terms of radiation, is Chernobyl, which happened in the late 1980s. There was a plant in Ukraine that had a runaway reactor. It melted the plant, and all the nuclear material is still sitting there just going. And they literally put millions of tons of concrete on top of it to try to contain it. But the exposure from that sent radiation in the air, and 75% of Eastern Europe was exposed to that radioactive cloud. Now, there's a couple of things about it. I mean, that radiation that's there is going to be there because it's a long-lived isotope that's involved in that reactor. It's going to be there millions of years. So that problem, it's there. And until we devise robots that could go in and clean it up, any human that goes in there is going to be dead in a matter of hours. They'll get a lethal dose of radiation. We're either just going to have to keep it contained the best that we can. The thing that's surprising about Chernobyl, and we really are redefining how we look at this, is the way that nature repaired itself. Okay, because our prediction is that the amount of radiation, that, and we're going to talk about terms of radiation and how you talk about exposure in just a couple of slides, but there were lethal doses 1,000-fold for everything around. That should be a sterile environment, and there should be nothing living, any organism living, in terms of what we thought was radiation, within 20 miles of that. Everything should be dead. And if we look today, if you go to Chernobyl, and the wildlife's thriving, the trees are growing, and we're redefining what we thought we understood about radiation exposure with that event. Because Mother Nature is self-repairing damage that's been caused by radiation in a way we didn't think that was possible. And we're studying that actively. How can we look at that way Mother Nature is somehow repairing nuclei that are DNA that's being damaged by radioactive events? How's it repairing that so quickly? And how can we use that repair process to solve other diseases? It's actually opened up a new study, a new field to us. But it's one of those things, every time we think we have a clear understanding, we create a scientific law, something happens and goes, it's an uh-oh event. And that's an uh-oh event for us. We didn't really understand everything we thought we understood. All right, there's a kinetics equation. We're not going to go into that. One of the things that I mentioned earlier, I just want to mention, is looking at radiocarbon dating a little bit more in detail. So anything that was once alive contains carbon in it at some degree. And when you look at carbon, carbon exists as either C12, C13, or C14. C12 and C13 are stable. The C14 is the radioactive isotope. And I just mentioned it had a half-life of a little over 5,000 years. So what happens in the atmosphere, the chemistry of exposing the C14 atoms or the carbon atoms to the alpha particles or the gamma radiation that comes in from the sun, it keeps the rate of decay the same. But something, as soon as it gets not exposed to the atmosphere, it starts to lose that ratio of C13, starts to decompose. So we look at the ratio. We use an instrument called a mass spectrometer to look at the different ratios of C14 to C12. And basically the way that this is done is you take a sample that has some carbon in it and you burn it in the presence of oxygen. And any carbon that's in there gets converted into CO2. And some of the CO2 is going to be normal CO2, C12, but occasionally you're going to have one of these heavy CO2 atoms. And you take an instrument that can measure a molecule at a time and count the ratio of the two things. That's what the mass spectrometer does. So we compare the ratio of these particular types of atoms. And we can, from that, we can get a good estimate. Typically, we used to say the number was 20%. Now we're easily at 10% of accuracy as how long has it been since this form of carbon has been exposed to the upper atmosphere. There's a limitation to it, though, and the book says it's around 50,000 years. I think today we argue it's closer to 100,000 years. That after about 9 half-lives, the radioactivity from C14 is almost at the background level. Now we got a little bit better instruments, and we can push that number back a little bit further. And we'll probably be able to push it back a little further than that. But for things that are older, like in rocks and petrified materials, there's other isotopes that we can look at in the same way. All right, so we use carbon dating for young things and things that are going back to what we think of as prehistoric times, 100,000 years back and further. We can use one of a number of different isotopes to describe that. So other things that we look at are things like uranium-238 ratio, and we look at that's ratios to lead inside of rocks. And we know something about the decay that occurs on these things. We can compare that to the volcanic rock, to that in meteorites, and look at the differences between the two. From that, that's how we've estimated the age of the Earth to be somewhere in the neighborhood of 4 to 4.5 billion years old. And this is one of the conflicts that we have with the Bible, which if you strictly interpret the Bible, it says it's 5,700 years old. All right, so there's a scientific mismatch that we have. And if we look at the age of the sun, we think the sun is probably about 500 million years older than the Earth. All right, so the Earth was formed shortly after the sun, and we think the universe, in terms of putting an age on the Big Bang, so if we look at all the radioactive elements that would have been created in the original Big Bang, all of those point back to about 1 billion. So from our understanding of time, time zero is 14 billion years ago. The Big Bang occurred. Now that's the most accepted theory in science, and I'll say that it's a theory. This is something we have no way of going back and seeing that, but that's based on the expansion of the universe, looking at radioactive decay. It's looking at echoes of the original Big Bang explosion that occurred. They all seem to point back to a common clock about 14 billion years ago. Has this happened 1,000 times before? The universe has exploded, condensed, exploded, condensed. We have no idea. Only thing we know is what happened, what we think happened 14 billion years ago. And there may be some scientific discovery with the next telescope that goes into space that says we're all wrong. Because that's the way science works. You make your law based on the data that you have, but you're constantly trying to prove and disprove that. You're trying to test it against the latest technology. So we think the universe that's our magic number we're close to. All right, the things we wish we could undo. One of those is nuclear fusion, and we wish we could do a lot more fission. So we talked about the things like the radioactivity that's around from atomic bombs. So some of the nuclear events are fission events, and that fission event is when you take a very large nucleus and you break it into smaller chunks, and you get off some energy associated with that. And these smaller chunks, all these daughter nuclei from the reaction, are typically radioactive for thousands and thousands of years. All right, so you have the possibility of generations of people being exposed to radiation events, and that can harm their health. With fusion, what happens is that small nuclei can be crammed together to make something larger. And the good thing about the fusion, this is what happens in the sun. The sun is primarily composed of the lightest element, hydrogen. And the way the sun works is that there's so much matter there, gravity squeezes down so hard that the atoms of hydrogen come together to make helium. And when they make helium, it gives off the energy, and it gives off a lot of energy. To give you an idea of the temperature and pressure, it takes around 30 million degrees of temperature and a pressure of 10 to the 16th atmospheres to squeeze hydrogen atoms together. Those are big, big numbers. Otherwise, every car we'd be driving would have a fusion reactor in it. If we can figure out a way to make this event occur in conditions other than the sun, inside of the sun, we would solve our energy problems today. Both of them generate tremendous amounts of energy. Fusion events release more energy per gram than fission events. That's the reason this is the one we want to capture. There's a large reactor at Princeton University that's a fission reactor called the tokamak reactor, and they can do a fission event of that, and 24 hours later you can go in that thing, walk around. The radioactivity is back down in the background. For me, it's a tremendous amount of energy, and it takes it's not a break-even process. They can create this energy, but they have to put a bunch of energy into it to create those extreme conditions. What we want something is that it gives more energy out than we have to pump into it. All right, and we're still working on ways to do that sustained. So the materials that are fissionable, the most common one that's the concern is uranium-235. Now, of the uranium, less than 1% is uranium-235. And most of the uranium that comes out of the ground, 97% of it is uranium-238, which is non-fissionable, means it's you can't make a bomb out of it. There's not enough 235 in it to have a sustained chain reaction. So one of the processes that's going on is that you have to enrich uranium-238. You've got all of these different isotopes that are existing. You somehow have to pluck out an isotope at a time, the ones you want, and throw away the other ones. And this was actually one of the largest scientific achievements that's ever been accomplished, was the process of doing this in the Manhattan Project in Oak Ridge, Tennessee. So they designed and built huge centrifuges that they would take this gas and our uranium, they would convert it into a fluorine gas, which is volatile, and they would spin these atoms around in a way that a giant centrifuge, so that they only collected this uranium isotope. And it literally, the series of buildings, it's the largest construction project ever happened on the surface of the Earth. Each one of these centrifuges is the size of this building, and there were 4,000 of them built simultaneously. I mean, it is absolutely enormous what they did to create that. And it cost billions and billions of dollars. And hundreds of thousands of workers did it and didn't even know what they were building. I mean, they were doing construction projects. The whole Tennessee Valley Authority that was created and all the workers that did that. I mean, they created its own power grids. They created dams to supply electricity just to run these things. It was a enormous project to try to come up with this 235. Now, the problem is 235 can undergo a decay, and when it decays, it gives off a neutron. And this is where we hear the chain reaction. So when it gives off a neutron in its decay process, or when it reacts with a neutron, it gives off 3. So a neutron comes in, hits it, and it gives off 3. So if there's another one of the neutron or one of these atoms around, it's the chain reaction. It's going to be self-sustaining. So once it starts, it gets the critical mass and starts to decompose, it's going to keep occurring till all of the uranium atoms are gone, split up. All right. So what you do in a nuclear reactor is they take the fuel rods and they let a controlled amount of neutrons in a nuclear power plant, and they slowly, they try to control, they do have to control the kinetics of it, otherwise they're going to have a runaway reactor. So it takes a critical mass to get enough neutrons there. That mass is about 30 grams, okay, or 30 pounds of uranium. And you have to have a good chunk of it for 235. Otherwise, it's not enough to have enough neutrons to cause this vent to start. This is the big thing with Iran right now. It's a big thing with Korea. They're in the enrichment process, right? And North Korea has been successful to enrich it up. They've already detonated 4 nuclear weapons. So they're either getting their uranium-235 from somebody else, possibly Russia, or some other country selling it to them, or they built the technology and it's somewhere underground. We don't know where it is, but if it were above ground, we would have blown it up. The same way that Iran started doing these, started building them, and Iran started doing them, and they, the Ayatollah of Iran at the time said, Israel, you just wait. As soon as we get enough to make a bomb, we're dropping it on you. And Israel didn't wait for them to make the bomb. So every time that they've started to create these reactors that could do enrichment, Israel bombs the heck out of them. Okay, and they're trying to protect themselves from the development of these. It's one of the things that we wish we could undo in humanity. I mean, it's the potential for destruction. I mean, we think about it, it would be a tragedy if a nuclear weapon went off in Bryan County and there would be 20,000 people killed. That would be a tragedy. A nuclear weapon goes off in New York City or in Dallas-Fort Worth, 12 million people die. I mean, this is something that you can put in a large briefcase and deliver somewhere. It's things we could do without. We've got to figure out how to live together, country to country, without the threat of, don't touch me or I'm going to drop a nuclear weapon on you. That's a bully negotiation. And we're in the United States use it because we've got as much of them as anybody else. The thing that we have that gives us the upper hand is we have a superior technology to deliver it. We have stealth weapons and submarines that can hit any target in the world within an hour. So if somebody does something to us, we can retaliate. And other people can retaliate too. The problem is the possibility of a low threat nuke, of something that's a low tech. The concern is when the Soviet Union collapsed, the Soviet Union had in excess of 50,000 nuclear warheads that they built. Over 2,000 of them right now are unaccounted. We don't have an inventory, know where they are. So they're either in the countries that split off from them, and those countries are keeping them secret. There's no way some of them haven't been purchased by a rogue nation with the idea. The United States has an entire team that's part of secret agencies that they go out with millions of dollars and annually try to make purchases of enriched plutonium. They're trying to buy it. So they're trying to go out and buy all the black market bomb material. And then they arrest the people that do it, but they're doing sting operations. And if you go back and look at history, every year they make a couple of purchases. That stuff's out there.
What could kill 12 million people? The briefcase?
Yes. A thermonuclear device, absolutely. And it weighs 100 and something pounds. But yep. Russia actually developed what they call a suitcase nuclear weapon for that exact purpose. So if you didn't have nuclear detectors, could be smuggled in a briefcase, left somewhere, and that weapon, when it goes off, will vaporize everything within a 20-mile radius. I mean, you're talking about 200 million degrees in a matter of seconds. There's no running from it. You're instantaneously gone. That's a scary thought. That's something. That's the reason it's important to have rational leaders on all sides. You talk about something that can affect humanity so much. You've got to have peaceful discussions, and you've got to compromise. And there's got to be a way to. I mean, if you just keep making enough people mad by stepping on their toes, somebody eventually can hit you back. It's human nature. And if you're a small country that's got nothing to lose, when I say that, I've been to a couple of countries where I've done mission projects, and their standard of living is so low, they look at us with so much envy. Well, and y'all gripe about what? About the taxes you pay? And those are people where they're, even in Mexico, we went down, and I've done 3 trips to across the Mexican border where we took people, built what we would call a garden shed here out of center block homes where people were living in cardboard homes before. Because everybody was told in Mexico, if you come to the United States, there's everything here. And they get to the border and the border's closed, or there's not jobs for them. And they can't get a visa. So you've got by Reynosa, and in those areas, there are millions of people staged come into the United States, and there's no housing for them, there's no nothing. I mean, they're living in a absolute poverty that's unreal. And that type of event occurs in 75% of countries in the world. I mean, 1 in 3 people that are alive today go to bed hungry at night. That's the real world we live in. So somebody like that doesn't have a good reason to wake up every morning, that's in control, you give them a nuclear weapon and the possibility of hurting somebody is tremendous, whether it's their own people or they decide to retaliate against somebody else. So fission events have the chain reaction, so it becomes self-sustaining once it starts. You can't stop it. The key thing is you have to have enough of the material to start the reaction, and it's called the critical mass. And that's what we want to stop people from reaching that. This is the fission event. Nothing there that we need to see. Let's talk just a moment about nuclear power before we quit this. So if we look at nuclear fission, it creates a lot of energy associated with it, and we use that to generate electricity. So there is one on I-40 in Arkansas that's a fission plant. If you go into Texas, there's one outside of Austin. There's one outside of San Antonio. We haven't built a new plant in the United States in over 40 years, a new nuclear plant. We started doing it until an event that happened in New York at 3 Mile Island, and it was a release of some radioactive materials, and then the public said, "Oh, radiation's bad," and we've not proceeded in building another nuclear plant since then. We're 15 to 20% of our power comes from nuclear reactors, but if we go to other countries around the world, go to Japan, France, UK, they're almost 70%. And that's one of the things that makes us one of the worst offenders in terms of the CO2 world. We get 80% of our power derived from fossil fuels, whether it be coal, whether it be natural gas, or the consumption of petroleum in the form of some type of fossil fuel that kicks CO2 in the atmosphere. We're not that big of a population. We're 300 million people. Where you look at China is closer to 2 billion, and their emissions are substantially less than ours. It's because we have a very high standard of living. The heat from the reaction takes water, boils the water, that turns to steam, the steam runs turbines, that creates electricity, and as long as you can do it contained, keep the
the steam isolated, because the steam picks up radioactivity, and then usually you have an inner steam or liquid substance, and the thing that they're using most commonly now, it's not even water. They take and hit up lithium, and lithium melts, and because it's easier to control than steam, and then that heats up water, and the steam from that runs a turbine generator. We use a different design than what most of the other countries in the world use. France uses a different design for their reactors. They claim to be much more safe in terms of the way that they isolate the nuclear reactor from external use. We don't agree with them in the United States. They've never had a nuclear accident. So maybe we should listen more to them. But all of these things are in some kind of this containment dome. It's a couple of foot thick of concrete. As long as everything stays in there, everybody's happy around it. And you can be feet from this building, and there's no radiation. The problem that happens, like in Japan, the tsunami hit, a 40-foot tidal wave came in and put a crack in this building. Right? It offset this reactor, and it broke the core of the reactor open. Now you got radiation leaking out there. And what do we do about that? How do you control it? In Japan, people went in and sacrificed their lives to go inside of the building, repair the reactor, knowing that they're being exposed to lethal doses of radiation, probably going to be dead within 30 days. At least 100 people did that. Okay, those are heroes to the rest of us, that knowing what you went in to do. That's just the way if you don't, you're going to have a lot of issues. So just looking at the dilemma, what do we do? A nuclear reactor consumes about 50 kilograms of nuclear fuel a year to power the electricity of the United States standard of 1 million people. And as long as it's contained, there's absolutely no air population or pollution. An equivalent for 1 million people is 2 million kilograms of fossil fuels. Okay, and if you remember what we talked about at the start of Gen Chem 1, the conversion factor from the amount of fossil fuels to the amount of CO2 in the atmosphere, because you gain 2 oxygen molecules, this produces 14 million, so 14 times 10 to the 6th kilograms of CO2 for 1 million people. That's the reason the CO2 atmosphere is rising without a doubt. It also produces things that are associated with acid rain. The biggest concern right now with us is CO2 causing the warming of the surface of the Earth, contributed to greenhouse gases. There can be the scientific debate on whether or not global warming is occurring, and it's occurring is a fact. Is it man-made? Is the only discussion there is to have. All right. Can we reverse it? All right. So can we do something to cut down the CO2 emissions? Freaky things are happening in weather that never happened. I mean, the examples of the flooding that happened in South Texas this year, in our recorded history, have been in the United States. We've never had flooding like happened this year. All right. The hurricanes, the most recent things is the northeasterns that struck the East Coast. They were talking about places in New Hampshire that got 26 feet of snow this year. Okay? And those were places that 100 years ago were getting 3 feet of snow a year. I mean, you've got to figure out what the impact of something like that is. All right. The rest of the slides are just things read over at your interest. Some of them will help you do the mastering chemistry problems. I'm going to switch down, and we're going to spend the next 30 minutes or so talking about the study of the final exam. Okay, so I would tell you the mastering chemistry is posted for chapter 20. 6 problems. That's it. So you can replace one of your lower grades by doing that homework set. All right. The other thing that I posted for bonus points is there's a speaker going to be here this afternoon. I know it's short notice, but his flight got changed. We were trying to hire a candidate to be an inorganic chemist. He's coming to us from the University of Maine. and he's going to give a seminar at 3 to 4. So if you come to that, I'm going to put a sign-up sheet for my students. We're coming up with a questionnaire that we're just asking students. I'll email you the questionnaire. It'll be like 5 questions. What do you think about this person? Is he going to be a good teacher? That's the type of feedback we want from students. Can you understand him? All right. Is he clear in what he's trying to tell you, articulate? All right. So
Where's that at?
that will be in S202. So you got an email on it. It's this afternoon from 3 to 4. So just find the sign-up sheet at the front of the room if you come to that. So it's 5 exam points. Some of you don't need exam points. Some of you want a few. All right. On Monday, there's going to be another speaker, but I don't have a schedule for him yet. As soon as I have it, if I get that tomorrow, I'll send another email out on it. You'll have the same opportunity to come to that one. It'll probably be Monday afternoon. All right, so depending if you're on campus next week. So final exam for us is going to be on Wednesday, 11:30 to 1:30, so the normal time that we meet. So the things that out of the book are chapters 10 through 20. And if you look at the Exam Institute, I'll come back to this in a second. These are the topics that they say that are going to be there. So physical properties, talking about intermolecular forces, phase changes and phases, kinetics, equilibrium, acid-base chemistry, and then electrochemistry. Now this is different this year because it doesn't used to. Last year the word radioactivity was down there. So I can't tell you. I haven't seen the new test yet, so I don't know if there's going to be anything on chapter 20 or not, to be honest with you. Right, so I'm going to assume there's going to be just a couple of questions on chapter 20. I'd say it's worth your while to at least look at it a little bit. So that's the unknown that I have for you. All right, in terms of the study guide, so this is the study guide that's posted. The things that we talked about in class, the things I suggest you look at is look at the chapter summaries at the end of the chapters. If you want to spend some time to review, go watch all the videos in every chapter that the author does. Those are outstanding little videos that he does to introduce a topic that are anywhere from 2 to 5 minutes in length. And they'll refresh your mind on what we did a couple of months ago. All right, so I'd encourage you to look at those. You can go back and look at any of the notes for the semester on Blackboard. All the videos for the entire year, including what we're doing today, are going to be available on Blackboard as well. And we're going to talk about the big thing that you've got to adapt to is now you don't get an equation sheet. All right, so we're going to talk about some key equations that you need to know, and we'll do those at the end here in a second. So the test that you're taking is the second term chemistry. So I know some of you bought the study guide from the ACS student group last year. Those are still available. I don't know how many they are. They have, were they 25, 20, what did they cost last year? Who bought one?
I think it's 20.
20, I think. So it's the same one will work if you bought one last semester or if you have access to one. It's the same guide. So it's a 2-semester thing. So if you want one of those, you can talk to Dr. Paiva or any of the ACS officers, and they can get you one. But again, the topics are the ones that I just listed. If you show up with a programmable calculator, I'm going to take it from you. I'm going to hand you something. So learn how to use something else. Okay, so you've got to. I don't even know if the new test is 60 questions or 70. Okay, in Gen Chem 1 it was 70. Last one we had in here it was 60. So I don't know what our new one is yet. I haven't even picked it up to look at it. You'll need a pencil, calculator, a Scantron. It's 15% of your grade. That's a chunk. You can invest by studying that. Okay, so here is a sample of an old exam. This is from '97, and this is a year-long exam. So we're going to go over this just to look at the style of questions that you're going to see. And then I've highlighted the questions that are relevant to us. So when they first started writing these exams, there wasn't a first semester chemistry, a second semester chemistry. You just took it at the end of 2-semester sequence, and it was available. Now they've broken it up into semesters. So don't write on I'm just going to go over the directions. Don't write in the test book. You're going to make me mad. Right? I'm going to make you put the serial number on your Scantron so that if you write it in the book and I have to go back and manually erase it because that's my responsibility, I'm going to penalize you some points for it. All right, I'll give you all the scratch paper you want. Just don't write in the test book, okay? You've got to turn in your scratch paper. Everything has to be turned back in. And one of the problems that's happened with these exams is that some faculty members at other institutions have not monitored their students. Students have got cell phones out, took pictures, sold those pictures to K. And the exam institute has to recall an exam once that information is publicly available, and they have to rewrite the exam, and then we have to start over again. It costs that university where they found the leak that came from about $250,000 because they have to pay for the recreation of that exam. You won't have a cell phone near these exams. Okay, everything will be on the back wall, and if you get a cell phone out, I'll come and take it from you. Okay, so if you have to have it on, you put it in the backpack, and just consider it you're unreachable during these 2 hours. And if there's something different where you have to be, bring your cell phone up here to me. If it goes off, you can go outside if there's some emergency. I understand. My mom was in ICU 2 days ago. I just picked her up from the hospital 10 minutes before I came from here. I understand emergencies happen, right? So if that's the case, bring me your phone. We'll deal with it. There's only one correct answer for each question. It's your responsibility to operate a Scantron form correctly. We've been taking Scantron tests all year, so you should have a good handle on that. It's also into your advantage to not leave anything blank. So on some tests, like if you're taking the GRE, if you don't know something, you skip the question. On this one, you take a guess. Whether you're A, B, C, D, yes, or any, mini, miny, mo, or you like C's as your favorite letter, whatever, don't leave anything blank because it's going to count against you if you do. Okay, so I'm quickly just going to show you some of the types of questions. So here was question 1. So look at shape. So you have a structure, and you got to go back to Vesper where we started the semester at. Remember that stuff? You got to do a Lewis structure, figure out how many lone pairs of electrons around the nucleus, and you got to predict, is it linear, tetrahedral, triangular, or bent? Okay? Remember that long ago? Yeah. Do or don't. And on this one, it's a similar type question. It says, which one has a similar Lewis structure to another compound? So not only you have to figure out the Lewis structure of ozone, you have to figure out the Lewis structure of these guys to figure out which one matches. Part of that, you can use similarities of the periodic table. All right, so what's in similar columns? And I'm not going to go through and work these. I'm just going to show you the type of questions there are. Which one's the most polar? Now, if I gave you this question on the test, I gave you a question like that, but I gave you the electronegativity table. No electronegativity table. But you remember fluorine, the top right-hand corner is the most electronegative, and everything tears away going down or over to the left. So from that combination, you can look at when you have anything that's a diatomic, it's completely nonpolar because the two things. So to find the most polar, you're looking at the things that are the extremes. The atoms that is furthest to the right combined with the one that's furthest to the left and furthest down. That's going to be the most polar. All right. Something about hydrochloride gas, recognizing what its polarity is, what happens when it dissolves in water. All right. So on this one, it's wanting you to recognize that it's a polar compound that dissolves in water. You also have to recognize it's a strong acid, and as a strong acid, completely associates into its constituent ions. All right. Spontaneity. So talk about things in terms of spontaneity. This is the last chapter, or the chapter that we looked at on thermochemistry. Look at these processes and say which one is going to be the most spontaneous. Which one is going to have a negative change in entropy? You got an exam question just like that. Look at a reaction and tell me something about the free energy to tell me if it's going to be spontaneous at, let's see, I got to read the question. Okay, it indicates that it is spontaneous at room temperature. And then it wants you to tell us something about, is it at equilibrium? Is it reversible? What do we know about that? Something about an energy level diagram, talking about activation energy. Okay, so this was the activation energy, the hump or the barrier that we had to go over. And what does that tell us about a reaction? Is it endothermic, exothermic, etc.? A rate reaction. So if we look at a particular reaction and we want to know what is the expected rate law, so it tells us something about the reaction and what can we do to predict this. All right, here's the problem I have with this question. You can't. So some goofballs wrote this test question, and you can't answer that without doing experimentation. You cannot look at stoichiometry and tell anything about what the order of a reaction is. That has to be determined experimentally. Okay, so that's a crappy question, and sometimes those things make it through. All right, here's another energy level diagram talking about what does a catalyst do to the system. Here's something it's talking about radioactivity, but it's applying to first order kinetics, but you just have to understand what half-life means. So if a half-life is 14 days, how long would it take for the radiation to fall below 6.5%? So you figure out, okay, how long does it take to go to half? Then half of that's a quarter, half of that is a 12.5, and then half of that again. Right? So you calculate how many half-lives that's going to be. Talking about the collision theory associated with kinetics. We talked about that in class. A redox reaction. And in this particular one, it's talking about you've got a certain amount of the number of moles of one reactant that's being produced, and you want to relate that back to one of the reactants, the number of moles of reactants. It's a stoichiometry question. Here it wants you to look at the initial rate laws just like we did in the lab, and it wants you to come up with the rate data. You look at the different concentrations and the rates that are produced. From that, you find out, is it zero order, first order, or second order for both of the reactants. So you look at the one thing that's changing, whether it's reactant A or reactant B, and how does the change in concentration influence the change in the initial rate. Okay, so that's a probable question. What does it mean for something to have a certain order? Naming, we did just a little bit of this as we went through the semester of some hydrocarbons, but not much. Actually, the next chapter in the textbook is chapter 22. Chapter 21 is organic chemistry. But if you look at the description, organic naming is not on the topic list anymore. So I don't think this is a valid question anymore. I wouldn't waste my time studying chapter 21. What happens when water evaporates? Okay, so I would expect 100% of you to be able to answer that question. So what happens if, which one would form a precipitate? Those dang solubility rules. I'd like to say damn, but I'm not supposed to say that in class. Those dang solubility rules. Which one forms solubles and which one forms insolubles? Okay, what one forms a precipitate? Okay, so sulfides form precipitates most of the time, so that's the one that would precipitate out. And there are things that never form precipitates. Nitrates never precipitate out. We know HCl and NaOH, that's water soluble. Nitrates don't precipitate out. So you can look for the keys, and those are the nevers. Those answer those questions. Look for things that never form precipitates. That's the way you approach those questions. All right, a gas cylinder removable piston. Okay, so which one is going to increase the volume? So that's an ideal guess. That's not a chapter 2 one. Lattice energy. That topic we talked about a little bit with the molecular forces chapter and phase changes. That's what that's dealing with. You've got a salt solution. and you need to dilute it. How much do I need to dilute it? CV equals CV. We did that in lab umpteen times. If you got a sample of gas and you got to compare these two gases, and both of them have the same kinetic energy, what does that mean in terms of the physical terms? And we talked a little bit about that with the energy chapter. Write the equilibrium constant. You're going to have one of those types of problems. Write the K. What is a conjugate acid or a conjugate base? You're going to have one of those types of problems more than likely. And which one of these is the percent ionization for formic acid the lowest? And there's some different combinations. So understanding weak acids, weak bases. Chemical reactions that can occur. What it means for an equilibrium constant. So this one's actually solving the ice. You got to set up an ice for a system and solve that. Which one makes a good buffer? We talked about that. What type of titration is it? So in this case, it's a acetic acid, which is a weak acid. Sodium hydroxide is a strong base. Which one of those represents that titration? Are there any of them you could eliminate? The term we use is distractors, things it can't be. So I'm starting with acetic acid, and I'm titrating with sodium hydroxide, NaOH. Say again? Okay, why? I like your train of thought. Starting at a high pH. So if I'm starting with an acid, it's going to be something starting at low pH. So if I'm not sure, I can at least knock out those two. And now I'm guessing between two. My odds are much better. If I look at those, which one should it be? This is the one that forms the buffer region. So what happens with weak acids is they don't completely ionize. With a strong acid, it completely ionizes. Remember your pH lab. If you had the solution that was 10th molar hydrochloric acid, it was down below pH 2, your highest concentration. Where the 10th molar acetic acid was well above pH 3. Right? So weak acids, that's the hint. That you just need to understand that weak acids partially ionize. What we just did, a galvanic cell, which one, what's being reduced in that system, electrochemistry? An unbalanced reaction. Balance that sucker. So, yeah. Tell me something about E naught versus delta G. If it's positive, what does that mean about delta G? What would be one that's going to react in terms of electrochemistry? Which ones would proceed? There's going to have to be a standard electropotential table that's given to it. So actually in the front of this test, there was a list of about 10 redox reactions you could go look at. Which one of these requires a reducing agent? It's going to be the one that's going to be a redox reaction. So you have to figure out which one that's a redox reaction. Looking at the electrolysis, I'd say 55 would be a maybe question for us. We really didn't talk about that. That's in the chapter, but we didn't go there. All right, so which one's going to be, what's going to be the reaction for the spontaneous system? So what's E naught a cell? You should be able to do that. Talking about ionization energies and electron affinities, we talked about that a little bit. What makes transition elements different from other elements? We talked about that just a little bit at the start of the semester, not much. Identifying the larger species. That's probably Gen Chem 1. I'd say that's not a topic. Characteristics of metals. We talked about why metals are good conductors. Then there's a section over experimental stuff. So this one they're looking at concentration versus time to learn something about the kinetics. So what does it tell us what's going on with that system? If you have a multi-step synthesis, it requires heat. What does that tell us? Or what are we doing with that? Or why are we doing it? How do we do it? Even something as simple as reading a burette. I know this is a challenge because some of you struggled like crazy in this lab. It's the last lab we did with the vinegar. You've got an initial volume and a final volume. How much was delivered from that? And this one, you actually have to estimate it to the nearest 100th instead of the nearest 1/10th. But can you read the ruler if you think of it right and subtract the two? It seems so trivial. It doesn't always work that way. How would you best deliver 25 mils? And the key thing is how many significant digits are there. You can't deliver 25.00 with a graduated silver. Got to use something else. All right. When the temperature of a solution changes, what's that going to impact or change in the system? Why do we use the rule of add acid? We talked about this at the start of the semester, and every time we used acids, I went over that. Why in the safety is it important to add acids and not add water to acids? Okay, so the last thing I've done is I've taken all the tables, and I'm going to tell you the key equations that you ought to invest some time in to know. All right? So, things you should know. You are not going to be asked to do a Clausius-Clapeyron equation problem. Okay? You certainly should be able to do a specific heat problem. All right? So this is I'm going to go green with things I would invest in knowing. Specific heat. Those conversions. You certainly need to be able to go from Celsius to Kelvin. All right? The constants like R are given in the front. So all the constants are given in the table. The electronegativities are not given, but you need to at least know the trends. You need to know where the least or the most electronegative is, and that's fluorine. Okay. Henry's law. That's a really simple equation, easy to apply. Definitely, you've got to know the dilution equation and how to calculate moles. Rayleigh's law. If you're doing the pressure of a solvent with a mole fraction, you need to understand what happens with mixtures of gases. So the total pressure of a gas is equal to the combination of all the gases that are there. You may be asked to do something with the freezing point depression or the boiling point elevation, but again, that's a very simple equation. It's the molality times the constant. You will not have to calculate something with the Arrhenius equation. So that won't be, I don't think there's any way they would ask you to calculate either one of those. Again, I hadn't seen the test. You need to know how to do molarity, how to do molality, mole fractions, mole percents, and at least parts by 100, the percentage. You need to know those should be things that you tattoo somewhere. All right, the thing I tell you on the rate laws is at least know what it means to be first order. Understand that, or zero order, first order, and going down the bottom of the page that's not shown is second order. Know which ones are linear with respect to what you have to plot. If it's linear with natural law or concentration versus time, that means it's zero order. If it's linear with respect to natural log of concentration versus time, that's first order. And then if it's linear with the inverse of concentration versus time, that's a second order. I tell you, if any of them know the first order rate equation for a half-life, I think it'd be pushing it to ask you to memorize those. But key thing is understand what does it mean to be second order, first order, or zero order in a system. Okay? All right, let's go back to next chapter here. All right, and we just got a couple of minutes left. So know the relationships, know how to write a K value. Remember that solids and pure liquids don't appear. Okay, just things that are going to be in solutions. If it's gases, you substitute the pressure in atmospheres. That if we invert the equation, we invert the value of K. The gas constant will be given. That's a maybe. I don't know if they're going to ask you to convert a K sub P to K sub C. I don't think I remember seeing that. You will have to do something with a Ka to Kb calculation. Things with pH, understanding that the Ka or Kw is equal to H plus times OH minus. If you're given one, you can solve for the other. Be able to go from pH to H plus and OH minus to POH and vice versa. So you got to be able to do all those exchanges. If you're given a Ka, pKa is just the negative log of it. Remember the shortcut rule that you can use, pH plus POH is 14. And in terms of the weak acid, weak base equations, the simplified forms are going to work for you. You don't have to waste your time remember the quadratic. The simplified approximation is going to be good enough. H plus equals the square root of KaCHA. OH minus equals the square root of KBCD. The solubility equation, you're going to be asked to solve the solubility of something given the KSP. The buffer equation, you're going to be asked to give the pH of a buffer given the concentration. They may ask you a percent ionization. That's something we did. All right, this equation or this last unit that we had, more than likely you're going to have to calculate an entropy, a Gibbs free energy calculation, probably something where you're given both entropy and enthalpy, and you have to find out what delta G is in the system, or when you have to find out what that critical temperature is. When does it convert from spontaneous to non-spontaneous? Know the combinations of when something is going to be spontaneous at low or high temperatures, given a sign for delta G or for delta H and delta S. Right? E naught of cell, E cathode minus E anode. You know, I've seen different years where they put either of these questions on there. So if you're comfortable with them, memorize them. If you did them on the last test, I'd say spend the time to memorize those. If you didn't even get the answers right on the last test, I would work on the things you know. Okay, and then after you feel like you've capitalized on all that, go back and look at reviewing those. Probably going to have something about the Nernst equation in there. All right, so this is our Nernst equation in the form that we use it. They may ask you to give you an E of cell and calculate K, or go the other way. So the other thing, a shortened form of this will be given. All right, so it's probably going to be like 10 problems that are in there. Okay. What questions do y'all have? 15% of your tiny rate.
Thought it was
14% rate, yeah. I actually forgot to change that.
whole 1%.
But it could be your highest grade of the year. I'm expecting it to be the highest grade of the year for everyone. Okay, it's your opportunity to show me that even you didn't master it on the test, you figured it out by now. Okay, remember last year, 60% of the class is their highest grade of the year. And a couple of the students that it wasn't their highest grade, they were in a position where it didn't matter how good or how bad they did on the final, it wasn't going to change their grade. And I'll tell you, if you're in the same position, if you're in the middle of an A-B, or the middle of a B range where you do fairly good on the test, it's still not going to get you to an A, and you do pretty bad on the test, it's probably still not going to drag you down to a C. Study something else. Okay, spend your time wisely. But if you're borderline and need to go up, or you're close to falling down, invest some time and get ready for this test.
What's your curve?
Say again?
What's the curve?
Last year it was 41 questions. So out of the 70 questions on the test, it was 41.
Okay.
Was 100%. So if you made a 45, it was 45 divided by 41. And last year there were 5 out of 18 that made greater than 100 on the exam. But I don't expect everybody to make 100 on the exam. My goal is for you to be within a standard deviation unit of the national average. So if you get 30 right on it, you're going to be right at a 70 on the test. Okay? So some of you at 70 is the highest test grade of the year. I'm realistic. So which is where you are. It's an opportunity to improve, get better.